Okay, good afternoon, everyone. Welcome. And today we're very happy to have Professor Reza Azad-Daraksh here. Reza is a professor at Florida Atlantic University and also started PQ Secure Technologies. Today he will talk about supersingular isogeny key encapsulation in hardware.
Thank you. Hello, everybody. Thanks for the introduction. So today's talk is about post-quantum cryptography. SIKE is one of the candidates for quantum-safe cryptography submitted to NIST for standardization. So I would like to start. Okay. So quantum threat to information security is basically what we are busy, everybody these days, focusing on large-scale quantum computers will be able to break kind of some encryption systems. Basically, public key cryptography, signatures, and kind of symmetric key cryptography will be a little less secure. So we need to migrate to encryption to quantum-safe resistant algorithm. And the question is that when we should do that, when we should start. So assuming that we will get a quantum computer by 2030, which is, I'm very optimistic here, probably it's going to be a lot later than that date. But so NIST started a project called Post-Quantum Cryptography Project. And in that project, by 2017, they started round one of asking proposals, solicited for proposals for post-quantum cryptography and for basically public key cryptography, digital signatures, and also key exchange algorithms. And by 2019, NIST second round started. Out of 83 candidates, only 26 candidates went to the second round, including 17 from key exchange algorithms and basically 9 from digital signatures. So NIST is supposed to give out the first standardization draft by 2022. Industry is looking into adopting such algorithms for key exchange, for digital signatures or encryption, probably by that date. And today's talk is a little about giving awareness of why we should start now and what are the solutions for small and resource-constrained devices. So if there is a quantum-safe solution that we all trust and is going to be standardized by NIST by 2022 or 2023. So we need to be worried about the fact that is called harvest and decrypt. So which means that retroactive decryption of data which are people or governments, other agencies could download encrypted data currently, or it's happening, for example, by any date before 2023, currently 2019, 17, 16, and before. And when they get access to a quantum computer, they can decrypt the data, encrypted data. So forward secrecy will be threatened, and we need to take action as indicated by government agencies now rather than waiting, for example, by 2023. So there are some solutions that NIST is going to standardize, but we would like to see what post-quantum cryptography will do for us. So we need to answer these kind of questions: design better post-quantum crypto systems, improve classical and quantum attacks to study these crypto systems, pick parameter sizes, because you know that our life is changing with kind of technology as changes. IoT, connected devices, car-to-car communication, big impacts of the technology as we see in our lives. So we need to determine how these quantum-safe crypto solutions will work in our platforms. So we need to develop fast, efficient, and secure implementations and kind of integrate them into the existing infrastructures, because sometimes it takes a lot of time to migrate from these solutions to new quantum-safe solutions. So NIST is looking to these kind of mainly category of quantum-safe solutions. So I put them in key exchange and signatures. Key exchange is very important. We need to be worried actually now, right now, before even we get access to a quantum computer. But quantum safe signatures, probably we can wait until we get a quantum computer. And the reason is that we can't retroactively break an authentication. So if you get a quantum computer in 10 years, you can't go back and break. Or there are some applications actually people are talking about, for example, authenticated software updates from, for example, Microsoft or Apple or whatever. But for certain applications, for example, which is the discussion of this talk, we can hold off on these signatures until we get a quantum computer. But key exchange is the most important because we are actually could break confidentiality when we get access to quantum computers and we go back in 10 years, for example. So solutions are on this category: lattice-based cryptography, code-based cryptography, and isogeny-based cryptography. So I hope you guys are familiar of a little bit with these candidates, but my talk is basically on isogeny-based cryptography, and the solutions that we are talking are based on super singular isogeny-based key exchange or key encapsulation. So first super singular isogeny-based crypto system was in 2006 by Charles Goren and Lauter. And it was based on super singular isogeny actually for hash functions, which for the first time people started using I'm talking about isogeny graphs and mainly on super singular elliptic curves. In 2011, so by that time, I think David Zhao was a postdoc at Microsoft Research. And by 2011, he designed a crypto system for key exchange based on the super singular isogeny based, along with Luca Di Fio. Luca was also a postdoc at U Waterloo. And I also joined end of 2011, by December, U Waterloo. I started working implementation of isogeny based key exchange. So by 2017, super singular isogeny key encapsulation, which is SIKE, submitted to NIST standardization. Basically, as you can see, a bunch of people from universities, industries, and also startup companies collaborated together. And that's why you see only a candidate submitted to NIST from the isogeny cryptography. As opposed, you can see a lot of candidates from, for example, lattice-based cryptography. So I promise that it's going to be darker. So architecture selection, I'm a cryptographic engineer mainly. I focus on, although I did a postdoc at Pure Mathematics Department in Combinatorics and Optimization, but I also do a lot of implementations. I look into complexity analysis. And so moving forward, I'll explain the arithmetic operations of this crypto solution SIKE, and I will discuss the implementations. Before going there, I would like to talk about the platforms that we have. So platforms that we are dealing with, hardware-only platforms, hardware software platforms, and software-only platforms. For example, if we are implementing something in hardware, we are designing a coprocessor or crypto processor purely in hardware. So finite field arithmetic, which is underlying the computations of SIKE, basically will be, for example, computation on arithmetic, addition, multiplication, squaring, inversion, and many others. So in hardware software crypto system, we have a CPU, keys are stored there, and we have also some kind of coprocessor, crypto processor only for some kind of just part of arithmetic operations, not, for example, control unit, which controls what's going on, what's happening. And when we have software implementations, everything is purely done through our software. So, for example, you have a desktop computer, you write your code in C or assembly, and you implement here, which is called software only. Here we have kind of software and hardware. You have a desktop computer, and you have an accelerator to perform when you have intensive cryptographic computations. You go there, and hardware only is for the case that you have like only a smart card, you don't have operating system, and you just do everything in hardware. So there are benefits, advantages, and disadvantages of each, but not disadvantages. Well, actually, if you are supposed to get to the applications, you are supposed to have, for example, only hardware. You can have runs operating system over there. And that's why you kind of obligated to work on hardware only solution rather than, for example, hardware, software, or software only. So software only starting from is very flexible. Easily you can update the code because it's basically everything in software, that download and updates of everything will be like easy. Patching stuff will be quickly done. So hardware and software only is kind of something between an hardware only and software only. It gives you a little bit of trade-off between optimization cost and also hardware cost. And hardware only is mainly dedicated for applications which are intensive, as I mentioned, for high performance that you would like to consider, and you don't care about the hardware cost that could have happened. So FPGAs, or field programmable gate arrays, are devices that these devices are kind of helping us prototyping cryptographic solutions. These devices are providing us with the flexibility that we can reconfigure the computations, and they are also available for us. We don't need to be worried about the ASIC design process, which is going to take about a couple of months or years. Even if you'd like to do like the latest technology, probably still by 2019, it takes like a year if you'd like to do 7 nanometer that you guys are holding in your phone technology. But FPGAs are off the shelf available. You can do basically just with fastest FPGA, you just order it, buy it and start programming in it. So FPGAs are composed of a bunch of logic cells, programmable logic cells, routing matrices. Matrices you can see here, they have inputs and outputs, multiplication blocks here, as you could see, and embedded like other blocks, for example, for memory blocks and DSP units. They're designed mainly for image processing, but we're utilizing them also for computations. And the good thing is that sometimes they give us good performance if we do computations of cryptographic solutions using those DSPs. Sometimes it's not. So it's a little bit tricky designing and working with FPGAs when we do implementations. Inside these like logic cells, we have LUTs, lookup tables. Everything moving on is kind of a lookup table based implementation. So these lookup tables are programmable. Like we kind of can have 4 inputs and 1 output function can be implemented with LUTs, and we have ton of LUTs plus registers or kind of flip-flops for kind of timing, clock cycles, measurements, implementations are also available here for free. I mean, for mainly pipelining and getting high speed, high clock frequency operations. So if I compare FPGA very quickly with ASIC, ASIC is basically kind of, you can do design quickly. I mean, in FPGA, you can do your design very quickly. You can do reuse it for other applications. If you would like, you can reconfigure it. Short time to market, simpler design cycle is very fast, and you can reprogram it. You can also have hardware, software co-design together that I had in the previous slide. And ASICs are kind of, if you go to mass volume, we go actually ASIC. And basically, we do FPGA first, and if we do prototype and it works well, then we can decide if we are going to have ASIC design. But again, if the performance or the time of computation is the target, then it's kind of trade-off. We can always consider FPGAs because FPGAs could be a lot faster because you get access to the fastest tech and latest technology available rather than waiting for ASIC. So for design parameters for, hardware design are mainly security, silicon area. Area means that how much you occupy the silicon in your device. Kind of performance and kind of other design, for example, for time. Here, if you go talk about power and energy consumption, they're not similar. They're not same. Energy comes with time of computations. Power is kind of related mainly to silicon area, how many gates or transistors you're putting in your design. And that's all needs to be considered, for example, based on also secure implementations, which is very important for cryptographic applications. So moving forward, I'm going to talk a little bit about math of isogeny-based crypto. So if you remember for general elliptic curve cryptography, elliptic curve Diffie-Hellman, we are working basically Alice and Bob key exchange. We are interested, or elliptic curve digital signature. The only operation over there is a point addition or group operation, which we achieve point multiplication, and we do like scalar multiplication for Alice and Bob, and then they exchange, they do another point multiplication, and which is point multiplication can be break down to point addition and doubling, which is doubling is a special case of addition. And the hard problem is that giving a point P and the scalar of that point, for example, Kp, it is hard to find K. The hard problem is called elliptic curve discrete log problem. And we assume that with classical computers, it's hard or it's infeasible to solve that problem. So, but if there is quantum computer, that problem will be broken in minutes or seconds. So when quantum computer, I mean the logically, cryptographically relevant quantum computer. So the isogeny-based cryptography, in contrast, is based on a problem, is working on set of curves. And if we have two curves, E and E prime is an, assume for now, that image of that E, and finding the phi, the function that maps E to E prime, or E to E prime, is the hard problem for isogeny-based cryptography. So as you can see from here, for example, we can map point P from here to another curve phi of P with this function. And we can also map this curve, which is E, to another curve E prime, which is image of E. So given E and E prime, it's hard to find phi of E for classical computers and also for quantum computers. So this is conjecture that quantum computer, there is no actually quantum algorithm that can break this kind of crypto system. And so we are kind of widely accepted that this kind of crypto system could be one of the candidates for quantum safe cryptography submitted to NIST for standardization. So I would like to continue the discussion here with a toy example. I think that it's going to help us to understand and move forward when we go to talk about the implementations. So we are basically interested in a set of supersingular elliptic curves. Supersingular elliptic curves are basically a family of elliptic curves in contrast to ordinary elliptic curves. In the past, people tried to use ordinary elliptic curves for post-quantum key exchange, but has been failed, and there are kind of sub-exponential attack on them. We work on underlying field for supersingular elliptic curve isogeny is basically kind of we work on P of this shape. For example, P equal to 2 to the power of EA, 3 to the power of EB times F plus and minus 1. Which is a prime number. For example, I give a number example here to have you guys engaged. My prime is, for example, 71. I write in this form 2 to the power 3, 3 to the power 2, minus 1, which is like 8 times 9 minus 1 will be 72, 71. And there is a theorem says that all supersingular elliptic curves up to isogeny, they have number of points on that curve is P plus minus 1 squared. So number of points will be 72 squared here. And supersingular J invariance, which is the key thing here, so bear in mind here, I'll come back to that, is number of supersingular elliptic curves that isomorphic are P over 12. So if I have my P is 72, this number will be 72 over 12. Roughly, actually, will be 7. So for this prime supersingular elliptic curve isomorphic with this J invariant could be something like these curves here, 0, 17, 40. So I have 7 of those here. And I would like to use these and mention that how they can be used for, discuss the isogeny graphs can be used for key exchange. So assume that in this graph, which is connected kind of, I call it 2 isogeny graph. This one is called 3 isogeny graph. So vertices of this graph all isogenous elliptic curves over Fp squared. And the edges are, links between them are isogenies of degree L. So we have isogeny of degree 2 and we have isogeny of degree 3 here. with isogeny of degree L, we get connected of L plus 1 regular graph. For example, if it's 3 isogeny, we have a graph of the degree of each node is 4, and degree of each node here it will be 3, 2 plus 1. Okay? And we would like to see how we can use these kind of isogeny graphs for key exchange or like key exchange, and for real world kind of key secret sharing. So assume that Alice okay, sorry. So assume that Alice and Bob, they both they have access to this graph, and they would like to perform a key exchange. So Alice, for example, starts with the elliptic curve E0 over Fp squared. She chooses, for example, 2 points, random points, 2 points PA and QA, but the order of 2 to the power EA. Bob chooses 2 points from the curve that E0, 3 with the order of 3 to the power EB, and they're working on E0, which is the same curve public parameter for both parties. So an example of those points are, for example, given here. Alice chooses PA, QA, and PB, QB, and the curve, starting curve, for example, is E0 y squared x cubed plus x, which is a, for example, Montgomery kind of curve. So Alice and Bob also, they choose secrets. SA is the secret that Alice chooses from the set of 0 up to 2 to the power EA, and Bob chooses another secret, SP, to 0 up to the order of 3 to the power EB. Okay, for example, Alice chooses number 6, and Bob chooses number 3 here from that set. Okay, and we would like to see how they can perform isogeny walks, and then they do like key generation. So for key generation, Alice, starting from E0, Alice has a secret integer that she chose. She used that secret integer to compute a kernel for isogeny, which is PA plus, this is the point of Alice, the other point, she performs a kind of double point multiplication, uses that kernel and maps E0 to another curve. So we are getting image of E0, and we end up getting EA. Okay, which means actually Alice performs a walks on this graph. For example, Alice is starting from the 24. 24 is the J invariant of starting curve, which is y squared x cubed plus x. So Alice, which is below here, 2 to the power 3, takes 3 walks on this graph. So 1, 2, 3, and Bob does the same. So Bob's walks are 3 to the power 2. So 3 isogenies, but 2 walks, 1 and 2. So Bob ends up getting to the J invariant of an elliptic curve with J invariant 17, and Alice ends up to the J invariant of, for example, 14. So, and that's, so that 40 is the image of J invariant of the curve that is image of E0 with the secret kernel of the isogeny. So now Alice has EA 40, Bob has EB 17, and the public key that they would like to exchange, the public keys of each other, so is composed of EA, which is image of E0 over mod, the secret isogeny, plus image of 2 points of Bob on Alice's curve. So we have two images of Bob's points and the curve, and Bob does the same as well. Bob sends EB, which is the image of the curve that he gets with the secret isogeny, and images of 2 points of Alice. Okay, and then they exchange these data, information together. As you could see over there, attackers could see only EA, phi A of PB, phi A of QB. And the problem of being quantum safe is that given EA and E0 is hard to find the image, and the given also image of a point is again hard to find that function that maps that point to another point on the curve. So as you could see from here now, Alice is end up getting 40, Bob ends up getting 17, and so Bob will start with 17 and Alice will start from so Bob will start from 40, Alice will start from 17, and they will do the same. Okay, so moving forward, they change the curves because Alice got EA, Bob got EB, and then they will do again same thing with information that they got from each other. So from 17, Alice is going to do another 3 walks on the curve. So 1, 2, and 3. Alice gets to the J invariant of curve 41. And Bob does the same. So Bob starts from 40 and gets 2 walks on the graph. So 1 and then 2. So Bob ends up getting to 41, and then also Alice ends up getting 41, which is the J invariant of this curve EAB or EBA or E mod A mod B, and which we call it EAB. And this J invariant moving forward can be used for the shared secret between 2 parties of Alice and Bob. So this is the problem that has been studied basically from 2006, super singular isogeny graphs, and also 2011 for basic implementation of post-quantum key exchange algorithm, which later called super singular isogeny Diffie-Hellman. So for the real world, if I go back again for the slides that as you could see, numbers are, for example, 2 to the power 3, 3 to the power 2, 2 walks, 3 walks here. But for real-world applications, if we would like to stay secure against the quantum computers, for example, we would like to get security level of NIST level 1, assuming that is, for example, 128-bit security level, which is kind of classical security level 128-bit. So Alice needs to, the prime will look like something like this, 2 to the power of 216 and 3 to the power of 137. Which means Alice needs to do like E0, and then also walks 216 walks on the isogeny graph. Bob will do the same 137. And then they exchange the data, and then they get some kind of shared secret. So, which is kind of intense, requires a lot of computations, and as the level of security goes higher, for example 1, 2, 3, 5, and that number becomes bigger. So the prime size is something like 434 bit for the NIST level security 1, which requires our public key size to be only 330 bit, which is a special benefit of elliptic curve isogeny in comparison to the other quantum safe solutions, lattice-based cryptography, code-based cryptography. Key size is something about 1 megabyte. Or lattice-based cryptography for unstructured lattice, for example, being 10 kilobyte, or structured lattice to be like a 2 kilobyte rather than 200 bytes. So order of 10 times smaller key size. Isogeny graphs, actually, as you could see again from here. So I explained isogeny graphs over a small prime number with 7 nodes. This is actually coming from the paper, again, by Charles Goren and Lauter in 2006. It's an example, actually, for hash functions. And if I show you something like for SIKE, I think I pushed this wrong button a couple of times. It wasn't me. So SIKE 434, I can't even show you how many nodes are in my graph here. It's something about 2 to the power of 430 nodes of super singular isogenies, that if I would like to show how the security works, you figure out how it's going to be hard for classical computers to attack. So moving forward, I would like to talk about the computations of isogeny-based cryptography or super singular isogeny Diffie-Hellman key exchange. This pyramid is called pyramid of computations. We have similar pyramid for elliptic curve cryptography, starting from finite field arithmetic, going up elliptic curve Diffie-Hellman or elliptic curve digital signature algorithm or elliptic curve integrated encryption system. So all basic computations over here are mainly addition, multiplication, and inversion. So addition all over FP arithmetic, and then multiplication and inversion. If I go a little bit higher level, computations are FP square arithmetic. If you remember that, we defined all elliptic curve over for isogeny-based cryptography over FP squared, because it doesn't work on FP, and there is again sub-exponential attack. And FP squared computations, I'll show in the next slide. I think I have, so basically we can do addition, multiplication, squaring, and inversion using whatever we have over FP computations. Okay, so it's not a big deal if we have our FP arithmetic working, or if I have a hardware which performs addition, multiplication of those prime big numbers, I can easily implement also FP squared arithmetics based on the underlying field. So group operations here are point addition. Again, we have a lot of point addition, point doubling, and isogeny evaluation and computations. So isogeny evaluation and computations are mainly the ones that we are walking on the graph from E0 going to like ending up to EA. And I have next slides are coming. I have a little bit of animation about those. And then we get large degree isogeny graphs. Isogeny computations are basically because of Velou's formula in 1970, but the computations used to, people assume that they're very difficult. Takes exponential time, but actually computing large degree isogenies with small degree isogenies are a lot more efficient, as we could see from here. And then double point multiplication is the kernel computations for secret isogenies that we discussed. And we end up, I don't know what's going on here. And we end up getting to the post-quantum cryptography protocol, which is, for example, could be super singular isogeny Diffie-Hellman or SIKE or signatures and other possible algorithms in the future. So computation of large degree isogeny, as I mentioned, is a little bit complicated, but if we go perform them with small degree isogenies would be a lot faster. For example, starting from on top of the pyramid, I have R0, which is the secret isogeny kernel of the isogeny that I would like to map and then compute here, for example, R6. Or I have E0 and I would like to compute those isogenies, for example, phi, and I break down phi to phi 0, phi 5, phi 4, phi 3, phi 2, phi 1, and phi 0. Okay, and I have it here. Assuming that I would like to, again, I would like to give an example. E is equal to 7. I would like to compute this kind of isogeny, perform isogeny evaluation, and push E0 to, for example, is something here, E7. So again, I'm on the graph. I'm pushing E0 to E7. I'm walking on the graph, and I would like to show how we compute these isogenies. So order of E0 up there, E0 has an order of L to the power 7. I would like to multiply, instead of computing actually isogeny of degree 7, I compute several isogenies of degree L. So I multiply this R0 with something until I get order of R0 to be L. And then I perform isogeny evaluation. I map E0 to another curve, which is, for example, E1. And then I continue until I get here. So let's take a look. I multiply R0. R0 is my secret kernel isogeny of E0. Okay. I multiply it with L. L is, for example, my L is 2 to the power of 2 is like 2, right? Remember that for that example, I had 2 to the power 3, 3 to the power 2. And that's, we assume that is done in the Alice side. So I multiply with L several times. For example, look at the order. Order is getting done. L4, L3, L2, and L. So as soon as I get that order of secret isogeny, which is order L, I can map E0 to E1, and I get the isogeny phi 0, okay? And also I can apply here, I get phi 0, and then I get phi 0. I need to get all of these points until I get here. So if I continue here, and then I push also R0 isogeny point, I can get also isogeny evaluation on that R0, I get R1, okay? And then I do the same. So knowing this point actually here, getting from phi 0, I can perform another isogeny. I can evaluate E, and then I can get E2. So with E2, I can do similar thing here. I push R1 to R2. And from here, basically, I go to here, which is like order L of this R2. And since I got the secret isogeny of order L, I can map again E2. So, and then, so I get E3 moving forward, I can get E3, E4, and then I can continue all the way down here, I get E7, which is the main thing that I am looking, sorry, E is 7, and then I get up to E6, which is E0 to E6. Okay, I work on the graph, I get E6, and this is kind of, with this example, we mapped E0 to EA. Okay, Bob does the same, maps E0 to EB, and performing all of the computations, and then they do the key exchange, and then they do again at the end, they get, for example, E equal to AB. But that's very big, so as you get that E is going to be 237. Okay. So the good thing here is that when working in hardware, we can do a lot of them in parallel, and parallelization is the key thing in hardware. So if you could look into here, I have a high-level hardware architecture for super singular isogeny Diffie-Hellman. So my inputs, look at this as a box. My inputs are, E0 is the curve or curve coefficients. So E0, 2 points for Alice, PA and QA, 2 points for Bob, PB and QB. And they go to memory unit, and we perform kind of computations. Computations of up on the pyramid are basically large degree isogeny that you saw that, and then we broke down them, all of them, to small degree isogeny, and then we did like lower level arithmetic computation, point addition and doubling, and then FP square computation and FP. So FP, everything is done in ALU, arithmetic logic unit, is composed of addition and multiplication that goes in your hardware, and you do the computations. So I have here also random number generators, TRNG, kind of true random number generator that you name it if you'd like, and that could generate your random secret keys for Alice and Bob. Output of first round is EA, which is mapping again that pyramid E0 to EA, and then image of 2 points for Bob, which is phi of image of PB over Alice's curve and QB or again on Alice's curve. And then at the end, after key exchange, in round 2, for example, if this is for Alice, Alice gets also Bob's curve, they exchange. Alice, instead of EA, Alice sends EA, Alice gets EB, and Alice's points on Bob's curve image, and then performing the computation, at the end she gets, or Bob also gets JN variants of these two. So a little bit closer or lower level look into the architecture is something like this. So we get a kernel of isogeny. That kernel of isogeny is like R0 that I had on top of the pyramid, and then I push the curve E0 to EA. composed of multi-point with double point multiplication or three-ladder. Sometimes we call it computation, which you multiply S, the secret, with Q, and then you add with P. So same thing here, point of Alice, Q, 2 points for Alice, 2 points for Bob. And then after having the 3-point ladder computation, we get isogeny computations every time you map E0 to EA with this secret isogeny, which is RA. Okay, that's how we do, and that's done by Velu's formula. At the end, you get EA, phi A of PB, and phi A of QB. So computations again over FP squared, arithmetic over FP squared is composed of computations over FP. And for example, one addition over there costs you 2 addition in FP. One multiplication over there is kind of 3 multiplication plus some additions, for example, 5 additions. Squaring over there, 1 squaring is composed of 2 multiplication and 3 additions and so on. So that's not a big deal to consider. So the key thing in the computations that we have, I'll have, I think, number of operations in the next slides. Actually, we have a lot of multiplication. So how we can multiply these big numbers efficiently so that we could get highest possible clock frequency. So field multiplication is kind of, if you're familiar, we perform field multiplication and perform also reduction because we are working on finite field. Finite field basically is the underlying assumption for that we define elliptic curves over. And assuming that we are multiplying two like operands A and B of each of, for example, on the cryptographic side of anything for isogeny-based cryptography, and we do perform modulus of P is the prime that we had there, for example, 71 as the prime. So Montgomery multiplication, we found out that Montgomery multiplication is the most high performance one that we can perform the multiplication, and if we choose a right Montgomery multiplication, because there are 2 main types. So one is called CIOS, coarsely integrated operand scanning. The other one is FIOS, or finely integrated operand scanning. So CIOS, so before going here, form of primes that we use for isogeny-based cryptography, 2 to the power EA, 3 to the power EB. We have a lot of ones of the size of EA over there, which makes our life a lot easier in comparison to elliptic curve cryptography that we work on Montgomery multiplication and reduction, which gives us P prime to be 1 and also makes our computations hardware architecture a lot easier, and we can do a lot of computations PE when we do processing elements in processing elements that we could get highest clock frequency in parallel. So CIOS basically alternates between multiplication and reduction. So you do multiplication and then reduction. And we could get the critical path. Critical path means that from input to the output, number of levels of operations. So we have 1 multiplication and 1 addition for CIOS, and number of clock cycles are basically 4 times number of words. So if we work with FIOS, we kind of could parallelize multiplication and reduction, which is very important. And the critical path is a little bit longer, and it gives us 1 multiplication, 2 additions. 1 addition comes to our critical path, which makes little operating clock frequency a little bit lower. But it has less number of clock cycles. So number of clock cycles in comparison to CIOS is 3 times number of words. So again, it's kind of all trade-offs. We need to look into see how we are going to implement. And basically, the multiplication is schoolbook multiplication, is operand scanning and not product scanning. If you'd like to take a look, product scanning is not going to give us the operating clock frequency, and then it's going to be a lot of clock cycles. Looking into these processing elements, I have PE initial, I have other PEs that they perform the multiplication and also the reduction. We actually focused on FPGAs, mainly Vertex 7 FPGA family, and we used, for example, dedicated DSP blocks of W by W, for example, 18 by 18. And this is also an initial PE, the other PEs that we employed for designing the architecture to be systolic, because prime size is too big, and if I just multiply like school book multiplication and reduction, like let's say school book or ripple carry adder multiplier or carry save adder multiplier, that's going to take forever to do, and it's going to be huge. So, but systolic arrays gives us the opportunity to have them working in higher clock frequency. So I have here a little bit of blocks illustration of SIKE. So what I talked was about all super singular isogeny Diffie-Hellman. That's the key exchange, but SIKE is the one which is kind of more secure, let's put this way. It offers a higher security model, which is to avoid also the key reuse attacks introduced for kind of super singular isogeny Diffie-Hellman. So if we look into the SIKE, so for SIKE we have super singular isogeny key encapsulation. We assume that Alice encapsulates and Bob decapsulates. Okay. So assuming that key generation, Bob up there, as you could see, we have public parameters in green, Alice values in blue, and Bob's values in yellow. So here, remember that Bob's secret key is S sub B. Easily, Bob gets an isogeny, maps E0 to EB, and then Bob's public key easily can be generated. So EB phi B of phi sub B of PA and phi sub B of QA. Okay, that's the public key for Bob. And now we would like to perform now key encapsulation using Alice's secret message M. So Alice hashes. So Alice needs to get a secret R. She hashes that message M with public key of Bob that she receives. Okay? And then Alice also performs the isogeny. She easily maps Alice E0 to EA. As you could see on the isogeny portion up there. So Alice maps E0 to EA with that secret and then this secret isogeny. So E0 mod this secret isogeny. So basically operations are here based on isogeny of like super singular isogeny Diffie-Hellman. We just added some hash functions, computations to avoid those kind of attacks that mentioned. So and also we have also Alice has also Bob's public key. From here Alice can map whatever she got from Bob, which is EB, she can get easily EAB. And that's the secret that she got. She calculates with R, and that's the R multiplies secret isogeny. EB mod this will give us EAB. Okay, which is E mod A, E mod B mod A. So Alice's public key will be, so obviously Alice's EA, phi A of PB, image of Bob's points on Alice curves, two points actually, and then that's the Alice's public key. Okay, also Alice computes the hash here, Kechek or hash function of, so since we have EAB, we can easily get J invariant of EAB and then XOR it with message, so hash it here. After that, I would like to get the secret, shared secret that Alice computes with encapsulation. So shared secret for Alice will be hash of message M, PKA, and C. Okay, and then we decapsulate this for for the first time I used Microsoft PowerPoint because of this time. So key decapsulation happens here also in the Bob side, and as you could see, So I imagine that Bob gets here a ciphertext EBA. Bob computes from EA because Bob gets EA, right? Bob maps EA easily, EA mod secret, and this is Bob's secret S sub B. And Bob also computes the M prime, which is same message up there, hash of J invariant with C. We get R prime. R prime is hash of, assuming that M prime the message, public key of Bob. And also Bob could get the EA prime from here, because from R prime you map E0 to EA prime, which is Alice. We assume that Alice's curve, and then Alice's public key too. So we can easily verify here public key of Alice. So if public key of Alice is that the same thing that we got from hash and then the one that we got from here, then we can get also shared secret key for Bob, which is hash of M, PKA, and C. So they both get a shared secret key after all the computations here. As you could see, everything we're talking about are, so hash, computations of hash are just nothing in comparison to computation that we do for isogenies. Okay, even the hardware area is negligible actually. So whatever we have is like a big multiplier, big adders, and then they're mainly occupying the area for operations for like fast computations basically. So if we look into the what Alice and Bob are sending to each other, basically it's not actually in the real world, it's only X, because we are working in Montgomery curves here. So in Montgomery curves, they have a benefit that you can work only on X coordinates rather than working on Y coordinate as well. And you can recover Y coordinate at the end if you'd like. So instead of sending the other curve, so X of P, X of Q, and if you have also 3 points in the curve, you can generate that curve and you don't need to send EA along with, and that reduces the key size a little bit for public key size of the Alice and Bob that we were talking in comparison to the original proposed by David Zhao and Luca Diffie back in 2011. So computations here, for example, are actual implementations that we did, Haas CPU, like random number generator here, program RAM, and then SIKE accelerator. This is an accelerator for SIKE in hardware implementation, isogeny accelerator here, cache or hash implementations, the controller and memory or register files, which this isogeny accelerator itself could be implemented. Actually, we did like in FPGA with hardware and software co-design, which is arithmetic controller, arithmetic unit, which is like composed of a lot of multipliers, adders, and then memories here, and then computations. We basically did kind of all control unit done by an ARM Cortex A9, which is highly used in like FPGAs, like you know, system on chip FPGAs. So if I go to the number of operations here for SIKE level 2, which is based on SIKE P503, number of operations for 503, which gives us actually NIST level 2 security. Look at the computations that we have, number of additions or multiplications for only key generation, only 40,000 almost key generation, key encapsulation of something about 64,000 and decapsulation 69,000. See a lot of operations for multiplication. So as you could see that we need actually to have a fast and multiplier operating in higher clock frequency with less number of clock cycles to be able to get a good numbers. So first round of submission that we did for SIKE for fastest results are something about 3.35 milliseconds, which is not bad actually, although it occupies a little bit higher number of area. So NIST level 1 at that time used to be NIST level 3, 750, SIKE P751. Currently it's NIST level 5 because of some I think better understanding of how quantum computers and what we have availability in terms of quantum memory. So as you could see, area in terms of number of slices, number of multiplication units or DSP units we occupied, number of block RAMs. Operating clock frequency is something about 198 megahertz. Key generation takes 9 actually milliseconds. Encapsulation 16 milliseconds. Decapsulation 17 milliseconds. So if we are talking about, well, actually this is for high performance implementation, why you see a lot of big numbers over there. So this has got actually improved in the second round, I think. Not even actually second round. Before second round, we did this work. So second round numbers are going to be updated in our website of SIKE. So we reduced actually, again, NIST level 5, SIKE 751. So these numbers are a lot smaller than, I mean, like similar area, but the number from 33.35 reduced to 26.9 milliseconds. So, which is comparable to, for example, Frudochem and many others. So, looks in terms of timing. Remember that the post-quantum key exchange based on isogenes, which is somehow proposed in 2005 based on ordinary curves, were about something like 3 minutes. Okay, and now we're talking about 20-second only milliseconds. So key generation basically could be done offline, and we are considering encapsulation and decapsulation. And encapsulation and decapsulation, one of them is done in the IoT or resource constrained devices. Okay, if I compare utilization of my FPGA, this is a Vertex 7 FPGA. This is the device specific name. So if you look at here, number of slices that I occupy, which is the highest, I mean, think 16.19% only of what I have there. Okay, I'm not occupying even 100% of my slices. I can get a lot smaller FPGAs. For example, eFPGAs, I occupy that, the whole of that, and I get that running with highest clock frequency and the fastest technology. So number of flip-flops are only 5% I'm occupying. Not, I mean, although people are talking about that SIKE is too big, SIKE is slow, whatever, but that's not something that we're comparing, for example, the key size to RSA, okay, the computations. So, and even block RAMs, so just 3% of block RAMs are occupied. And we have, I mean, thousands of, 100,000s of flip-flops available in, I mean, a regular FPGA. This is not even, it's like a, I mean, general FPGA. It's not even high performance or like a super fast FPGA, okay? So here I have a little bit numbers for IoTs. As you could see here, in the, here I have numbers a little bit for SIKE running time implemented actually in my Google phone Pixel 3 ARM Cortex A53. Timing is about 67 milliseconds. Okay, SIKE, I'm talking about implementation of SIKE. So if I implement it in a hardware, RTX 7, which is recommended by NIST, my hardware will require 10 kilo slices, 10,000 slices, okay? So if I go something like a ASIC design, that's going to be different thing. So I'm not talking about ASIC at all because things are not comparable here. So look at the timing and the ARM Cortex A53 and here. Well, actually, if I go, I mean, 72, which is, for example, Apple iPhone, but I mean, they're getting a lot fancier, faster. So timing for my 10 kilo slices is something about 11 milliseconds. 11 milliseconds is almost about same thing as timing of Frudochem or lattice space crypto. If I go to IoT devices, ARM Cortex M4, Microsoft Azure Sphere devices are basically built on M4. So software implementation, this is very tiny. So it's something about 1.7 seconds. Okay, but we are assuming that on those devices, we're not going to have key exchange every single minute or a day or whatever hour. And that's the timing that we get. So we could offer to have again, Arctic 7 FPGA or probably ASIC. With this design for IoT, timing will be 200 milliseconds, occupying only 3 kilo slices. Okay, that's if I have a IoT device, so and then I don't want to eat all my batteries over there, I can implement it in hardware, and that's doable. 3 kilo slices here. I don't have 3 kilo slices in ARM Cortex-M of IoT devices, but I can offer ASIC design, and that's going to be something about 300,000, like 200,000 of kilo gate equivalent of silicon area usage. So, which is what Microchip is doing. Currently, Microchip is offering like IoT devices. You get like any data on the device goes to Google Cloud, and they have a special processor there just to performing the hardware accelerator for the design. So as a wrap up, the case for SIKE. So the post-quantum landscape is kind of uncharted territory. So the smallest scheme is the slowest, and the fastest scheme is the largest, unfortunately. It's not comparable to RSA than ECC. So compared with traditional cryptography, where the fastest scheme ECC is also the smallest, right? RSA is the slowest and also the biggest. But ECC gives you, we always say 256 key size, 128-bit fastest and the smallest. Hardware and software together. This situation introduces a new set of trade-offs. SIKE advantages will become more pronounced over time. So because over time, and the reason is that over time we get like, if we will require bigger key sizes. In 2010, we were obligated using ECC of 100, 80-bit security level, 163, and now we are like 128-bit security level. So recommended by governments, all countries, all over the world. SIKE disadvantages will become less pronounced over time. And disadvantages because hardware technology is getting better and better always. So, and there is also a variant of SIKE or SIDH called CSIDH, which I would like to say why not. CSIDH should be the focus because there is a clear sub-exponential attack, and also the computations over there is not constant time. We try to make it constant time. It's almost about 10 times slower than what we offer for SIKE or SIDH, and if you make it constant time, it's going to be 100 times slower. So although it offers smaller, again, smaller key size, instead of sending 3 parameters, you want to send only 1 parameter, but scale with security attacks is like horrible. So the future of SIKE in terms of computational cost. So we know that hardware gets faster over time because we get like, you know that every time we get Moore's law is kind of dead, but it's getting improved. Software also gets faster over time. This happens naturally and without effort to expenditure. An across-the-board performance increase reduces the performance penalty of SIKE. So in absolute terms. We can also spend more time, get fast hardware. We can easily do that. And certain expenditure, hardware acceleration provide good value per unit cost. So if I do like a dedicated hardware implementation of SIKE ASIC, I can make it even close, not a lot, a lot better than RSA, but about to be a couple of times bigger than ECC, which is possible and doable. And computational cost. So as hardware and software gets faster, attacks also get faster. So it means that attackers are, as mentioned, in 2010 key size, and then key size now is almost, we're getting double key size every 6 years. So it means that what's going to happen with all other crypto post-quantum candidates, for example, lattice-based crypto. Assume that, for example, again, I'm going back to Frodo-Chem. Key size for Frodo-Chem, NIST level 1 is something about 10 kilobyte. If there is an attack attacks are getting better on Frodo-Chem, key size will be something about 15K, 20K kilobyte. right? How about ECC? I mean, isogeny-based crypto, or excuse me, SIKE. So we are 200 bytes. 200 bytes, assume that we double it. It's going to be 400 bytes. It's not getting even closer to 1 kilobyte. Okay? So faster attacks require larger keys to counteract. And across the board, key size increase enlarges the communication cost. So for that Frudochem or lattice-based cryptography, 10 kilobyte moving from 10 kilobyte to 20 kilobyte is not going to fly in IoT or even applications because the bandwidth is limited. So car-to-car communications, bandwidth is not even allowing that to perform like larger key sizes. How much larger we're going to get like there? That's why code-based cryptography is out of discussion. I'm not even talking about that. How about isogeny-based cryptography? 2 kilo, like 400 byte or 500, half a kilo is a lot doable in terms of communication cost. Also notice that communication cost is a lot more expensive than computation cost because computing 1 bit or the time or energy or that you spend on encrypting a data is 100 times less than sending or transmitting 1 bit. Okay, that's communication cost is very expensive. Variance in communication channel is much higher than variance in cycle counts. So SIKE already wins today on desktop browsers when, well, actually Adam Langley, Google did some experiments and he figured out that SIKE is working properly on their Google Chrome recently and compared with Frudochem and also Entru. So I stop here actually. I hope to, if you guys have any question, I will be happy to address.
Any questions?
I have a question. So the choice of prime, like the 2 to the power, some high power times 3 to some high power, usually often people will write plus or minus 1. And so plus 1 has better properties from the point of view of the graph. You can make it undirected, it's a Ramanujan graph with great expansion, all of that. Minus 1, there's significantly different properties of the graph. So why do you use minus 1 instead of plus 1?
That's the SIKE choice that we wanted to make p plus 1 squared. I mean, that's the only thing. But in terms of implementation, I don't think that it's going to make a little difference right over there. So that's, I think that's also doable. But I don't see any, it's not going to change anything, right? We know that it's like in terms of the computations that we are performing down level. So,
so you could change it later on the fly without causing significant disruption?
Yes, yeah, you can do that, yeah.
Well, you have to.
Yeah, because we basically, we can easily, it's reconfigurable and then you can easily update your P. So that shouldn't be a problem, yeah. Yep, go ahead.
I was just going to say, if P is 1 mod 12, then you have to work a little bit to generate a supersingular elliptic curve. You have to do some kind of CM construction, and then you have to justify, like, why did I pick this CM curve versus, you know, Jeanne Graph 0 or something. I don't know.
Yeah, it gets back to P to 12 of lux. I mean, 0, 1, 2, or which one, So, but from computation point of view, I don't think that it's going to be a horrible thing. Yeah.
Thanks.
Yeah, no, it's a good question. Thank you. Any other questions?
I have a question about, so you said there's certain FPGA that is recommended by NIST. So what does that mean exactly?
Well, actually, NIST recommended for implementation to be uniform all over the globe because people are trying different platforms. For comparison, NIST is trying to see which one is faster, smaller, slower, whatever. Okay, they recommended to work on Arctic 7 FPGAs. It's a medium scale FPGA, not that high performance or not very slow. To prototype on that all kind of candidates to get a better sense. And also for IoT device, they recommended to stick with ARM Cortex M4 because you see that all over the place. I mean, IoT devices that people are using are Cortex M4 mainly. So But there are a lot of, government, for example, the DoD recommends to work on FPGAs of ultra scale plus super secure FPGAs. And then also the security levels are a lot higher too. So DoD's recent call for prototype of quantum safe security starts from NIST level 3. So which is going to be NIST level 3, 4, 5. And I think that's it's going to be a lot bigger even, which I think that's another thing about the key size problem for other candidates. Some also lattice-based crypto, off topic, but they don't even offer levels between 1 and 5. They have only, for example, New Hope. Okay.
So maybe a follow-up question is that, so how do you imagine that this work is being used in practice? Do you attach some FPGA to every device?
Well, no, actually. So if I would like to make this phone secure, I implement everything in software because it's fast enough. I perform in this device 10 milliseconds. Okay, which is good for me. If I can have it. So if the device is getting smaller, IoT device, ARM Cortex M4, I implement that it's going to be 2 seconds, a lot of energy consumption. I perform that put a little chip. It's a small silicon area. It's going to be like 100 milliseconds, some area. But that's going to be low energy and low power. And if I have like a large cluster of computers, financial institutions, I can easily implement everything in parallel, fast computations. I take that number down less than even 10 or 7 milliseconds. So we're not gonna. So FPGAs are basically for prototype. So because academia or currently, if I make a chip of, for example, a SIKE, implementing SIKE in whatever speed, that's not going to be attractive. I'm not selling that, and I got to wait in the line for chip manufacturing fabrication companies for about a year. So there is no point of doing that. So, but there are also embedded FPGAs that I can get from off the market for 7 nanometer. So the technology of ASIC on this phone is 7 nanometer. If I would like to get that 7 nanometer ASIC design, I got to stay in the line at least 3 years, 2 years, something. I can get it in 3 months, but they won't give me 7 nanometer. They'll give me 30 nanometer, sorry. So, but if I would like to get an FPGA with that technology, I can easily buy it tomorrow with 7 nanometer FPGAs, and then I can prototype on that thing. So, which is the very good benefit of FPGAs in comparison again to ASIC. So, and if I figure out everything is good, I'm ready. I can study side channel attacks, performance analysis, secure implementations. If I would like to add things around, I do that, and I'll be ready by another year or two. I start looking into ASIC implementations. So, yeah.
So Reza will be here today and tomorrow in case anyone wants to meet with him. Just either talk to him afterwards or come see me.
Okay, let's thank the speaker again.
Thank you very much.